All right, so there's 4 possible 3-phase configurations. We kind of talked about them already, but now I'm going to show them and I'm going to make the connections, and you should be able to kind of see what's going on here. So if I have a Y connected source and a Y connected load, right? That means, and I have, you can see that they're labeled here. There's A, B, B, C, C, and then the neutrals. These all connect one to the other by name. So A connects to A, B connects to B, C connects to C, and the neutral connects to the neutral. Okay? And so if I analyze this circuit, you can see that what I'm going to be interested in, of course, are the line currents like I talked about. We're going to be interested in those currents, which, they'll show up over here. That would be IA, IB, and IC. And what's interesting about the Y to Y connection is that we can actually just analyze the circuit on a per phase basis, which basically means, because if you take a look at the loop, if I just want to use KVL, I have a connection from VAN all the way across here to a single load, Z1, and then back. And so I can use KVL and literally just redraw that circuit. Let me get my black, and I could write, VAN, a straight line to load Z1, and then this can be my neutral, but it doesn't even matter. And right there, I have IA, and I can analyze that circuit, right? Just like that. That's all I have to do. If I want to find IA, I would just say IA is going to be equal to VAN divided by Z1. It's just that simple, right? So that's the Y to Y connection. These are pretty straightforward. Y to Y is the easiest connection to analyze by far. And it's also very interesting to note that every other one of the other 3 combinations can be reduced to an equivalent Y to Y connection. I don't know if I'm going to have time to cover how to do that in this module because it's already gotten really long. But if you're interested in that, let me know. I think that it's not going to really matter, because if I'm going to ask you to solve one of these circuits, I'm not going to ask you to convert it to a Y to Y connection. You don't need to anyways. It's really just interesting to note. But this one is by far the easiest to analyze. Okay. Second, we have the delta to delta connection, which, equally straightforward. The A goes to the A, the B goes to the B, and the C goes to the C, just like that. And of course, I'm going to have a line current IA. It's going to show up here. A line current IB and a line current IC. But now, like I said, we're going to have something that's called phase currents, which aren't the same as our line currents that are going to flow through our load, because this is not going to be the same as IA or as IB, so they'll call this one IAB. This one would be called IAC or ICA, depending on the way you define it. And then this one will be called IBC or whatever. And those are your phase currents. And so someone, a problem might ask you to find IAB or IBC or IA, and all you have to do is determine, oh, if I need to find IA, that means I really need to find IAB and IAC and add them, because I know that IA is going to be equal to the sum of these 2 currents, because I can do KCL at this node, right? So everything we've learned already applies. Also, if you just wanted to find IAB, that would be very straightforward, because if you look again, we've got a voltage source, connected across a load and back. And so I can do a KVL loop right there, and I could just analyze that, that particular phase, VAB, to ZC and back. And the current that I would get here would be IAB. Note that there is another load here, right? ZC would be connected to ZB. So I can't say that this current here, this current here is not IAB. Rather, it's you know, this current is equal to the sum of these two currents. So I can't say that this current is equal to this current, but I do know that the voltage across ZC is VAB in this case. So I could say very easily that IAB is equal to VAB divided by ZC, and that would be correct, okay? It's just important to remember that KCL still applies, so we can't say that this current here is IAB. That's not IAB, that's IA. Okay, so that's important. This is why the delta ones get a little bit trickier to navigate, because we have to take that stuff into account. Okay, so we've gotten through the YY, we've gotten through the delta delta. Let's take a look at the Y delta. You know, not much is changing. We still have A to A, we have B to B, we have C to C. The neutral line doesn't get connected anywhere because there's nowhere to connect it on the delta load. And it just so happens that for balanced systems, which is what we're actually analyzing right now, the current on the neutral line is 0 anyway, so we don't need to worry about the neutral line ever. I drew it here as a dotted line, but if you add up the sum of the currents, IAB, you know, IAB, IA, or IA, IB, and IC, sorry, and you do KCL at this node right here, you will see that IA plus IB plus IC for a balanced system equals 0. And so if no current's flowing here, we basically don't need this wire at all, right? It might as well be open. So that's the reason why the neutral line doesn't really matter in these three-phase systems, which is another perk of using three-phase systems, right? You can eliminate one wire because the average currents for a balanced system through that wire is 0, so we don't even need it. Okay, so we've covered these two. The Y to delta connection, you know, similarly, I'm not going to, you know, go through these ones just as slow. I kind of need to get through this video here. But all you have to recognize is that, again, if I wanted to find the current through this ZC here, even though I have a Y connected source, notice the voltage across ZC. What voltage do I have here? It's VA. And the voltage I have here is VB, right? So if I wanted to find the current, that current that I drew in orange there, which would be IAB, again, I'd have to say VA minus VB over ZC, which is VAB over ZC. And so I'm sure you're starting to see that this is really just about figuring out what the voltage is across my elements of the load, and then determining using Ohm's law what the current is. It's really not all that tricky, right? Hopefully, at least, it's not all that tricky. This would be my line current IA, my line current IB, and so on, IC. And recall that this is called the phase current IAB, and I have phase currents for these two as well, and I can define them however I choose. Lastly, we have the delta to Y connection, and this is the last one, and then we're going to go ahead and pretty much wrap up this video. A goes to A, B goes to B. Again, we have nowhere to connect the neutral, so we don't bother about that. And then C goes to C, and we've got our line currents, and we have our phase currents. But you know, this time we again need to recognize something slightly different happens here. If I want to complete a loop here, I've got VAB, but VAB connects across Z1 and across Z2, right? So to create a circuit, I would have to go through both of these. And so I'd have to take that into account when I want to find this current, right? And so this is basically it for the configurations. Like I said, the book kind of asks you to memorize these in a sense. They're expecting you to just recognize that, you know, you can scale by √3 and try to memorize all the phases and this and that. I think that is a losing battle. I do not think that that's good, but I put this here anyways, just in case you want to reference this table. I have all this blank space here, and I'm not planning on using it. I just wanted to put this table in here from the book in case you're interested in looking at it and referencing it, and you don't want to go digging through the book for it. So this is, again, from the SATIQ 5th edition that I've been using for a lot of the figures for this set of slides. They talk about the positive sequence here. That's something I haven't talked about. If you have questions about that, let me know. It's really just depending on whether or not you say that your B source, right, is the one that has minus 120 degrees or plus 120 degrees. That's the difference between the positive and the negative sequence. It's really not a big deal. But yeah, just wanted to put this table here to summarize. You can derive all this. The book derives all this. I've loosely done some of this math, but I think it makes more sense to just look at the circuit and analyze it the same way that we would analyze any other circuit, and just use what we know rather than trying to memorize all these different equations, because I think that that's just not a battle that anyone's going to win. Okay, so I'm going to go ahead and end this video here, and I think after this we've got some example problems. Is that right? Yeah, so let's go ahead and start solving some example problems for three-phase circuits, and yeah, we'll wrap this module up pretty soon. Let's do some examples.